glad to have today Paul Wiegmann, number of graduates work in various fields of theoretical physics and initially belongs probably to London School. But today he will talk to us about hydrodynamics and anomalies.
Okay, thank you. So the story which I would like to tell you, so first of all, it's for physicists. So mathematicians will be lost in the first, after the first sentence. I'm sorry that I prepared for physics. Although the subject is rather formal and there is a lot of geometry in it, but it's for physicists. Yeah, so the subject is about hydrodynamics. And that is volume 6. No, I don't know. But and its relation to quantum field theory, but very particular corner of quantum field theory, which is called anomaly, or another name for its current algebra. That is volume 3, right?
25.
No, 4. So how these two subjects are related? That's what I would like to discuss. But looking for the audience, I understand that anomaly, which is classical part, fundamental part of quantum field theory, so the fundamental part, may be not known for this audience, so I will explain. But first, I would like to say the following. So quantum field theory counts about 100 years of development, right, since 1930s. Right. And we think that we know a lot of about quantum field theory. At least there are accelerators. They produce some observables, and they looks okay. Hydrodynamics is a different story, and it goes back to as a couple of million years, as long as mankind remember itself. And I just assure you that we know nothing about hydrodynamics, much more complicated. Nobody knows why Toyota engine works or why car moving. They're moving, the engine works. In the engine, there is a cylinder, there is a fluid, motion. Why it works, maybe Toyota engineers knows, but we don't. Every time you meet fluid, you understand how complicated motion is. So how these two things are related. That's what I would like to say to begin with. Quantum field theory is about motion of particles, but infinitely many particles. And we describe quantum field theory in terms of particles. We have creation operator, annihilation operator. We have asymptotic states where we can distinguish separate particles which run away and become distinct from each other. That's called asymptotic states. It's a theory of particles, quantum field theory, although it's an infinite number of particles, but it's a theory of particles. I think in 1959, Wiegmann suggested that there could be some situation, he thought about nuclear physics at that time, when in quantum field theory, which is theory of particles, could be described entirely in terms of currents. And currents is not particles. It's a vector fields which describe how media of particles moving. Relation between version of field theory which is described entirely by currents and by theory of quantum field theory, theory of particles, complicated and not identical at all. But there are some physical situations when everything could be written in terms of currents. I will mostly talk about Dirac particles, and let me call psi and psi bar the creation and the angulation operators. Then the current Dirac gamma matrices. Particles created by psi and by psi bar and angulated by psi, currents is bilinear. It's a different object. So under which circumstances is Gelman asked by currents? And that's how current algebra has been created, basically started from this question. Current algebra is a commutation relation between currents, which is supposed to be replaced everything, describe everything. Nowadays, but only now, quite substantial time after Gelman, we understand that a media which is described by currents is hydrodynamics. So this is the relation between quantum field theory and hydrodynamics. Quantum classical doesn't matter. Doesn't matter. One may be asking a question: under which circumstances media or infinite number of particles, quantum fields can be described by currents? The answer is only when these particles form a fluid. If it's fluid, it's hydrodynamics. But whether they form a fluid or not form a fluid, it's a physical question which needs to be sort of answered. Sometimes they do, sometimes they don't. Now the question what is fluid? Liquid and versus gas. What does quantum field theory describe, gas or fluid? In both cases, infinitely many particles, right? So it's a field theory, but is this liquid or fluid or gas? Very different substances. And sometimes gas becomes fluid, a fluid, sometimes not. But if it's fluid, then we are in this business and in this business. Okay, then now I would like to ask the audience, what is fluid? It's an interesting question. I practice this question every time I speak. And fluid is something which we deal every day. Everyone between us already deal with fluid at least half an hour ago. Right? What is fluid? A fluid could be compressible or incompressible. No, fluid is, if fluid would be incompressible, you will not able to hear sound in what? In what? Yeah, but well, how to formalize this? Gases could be very dense, but the distance between in gas distances between molecules are same as fluid. Could be so they pressure. Gas has pressure. And the answer is pretty complicated. Not immediate, and I would like to emphasize this, but it's kind of remarkable. The definition of fluid has been given in 60s. Vladimir Arnold. So he's probably the first person who said, "What is fluid?" Fluid is fluid motion, not fluid. Fluid motion, said Arnold, is the orbit of the action of group of diffeomorphism of space-time. It's a rather deep definition. I will explain what it is about. So it's about fluid is about classification of orbits of diffeomorphism of space-time. Let me explain what it means. For example, suppose I have a gas, and then the gas flow. Gas can flow in Ivan. If you hear and will do something else, you will waste your time. Yes, I suggest to do something else. It's not. Okay, then why you will miss this point? No. So suppose I have a cloud of gas. Then gas can flow in, say, in jets in different direction, making empty space here. You know that happened, right? But fluid cannot. No, then it stopped to be fluid. Because that flow assume discontinuity. So fluid is here, not fluid. Fluid never flow like that. And it's against of diffeomorphisms. Diffeomorphisms are smooth differential manifolds. So fluid never form breaks or empty space. Right? It's Arnold. So therefore, discussion about fluids must start from classification of orbits of group of diffeomorphism, which is a general mathematical question. Question is extremely complicated. Doesn't matter. Space-time. Yeah. It's extremely complicated question. And that is part of my story. Quantum field theory can describe gas and fluid equally well because it's about particles. But if we about fluid, that's subspace of quantum field theory, which is current algebra. Fluid described by currents only, not by motion of individual particles. Now, so I will speak about Euler equation, which describe inviscid fluid. Fluid could be viscid, there is viscosity, or could be nozzle viscosity. If it is viscosity, its equation fluid is called Navier-Stokes equation. Otherwise, it's Euler equation. So I would like to discuss Euler equation. If I remember correctly, written pretty long ago, and it's a partial differential equation. It's a first partial differential equation written by mankind, It's apparently a very fundamental equation which cannot be modified because it's related, as is understood 200 years ago by Arnold. It's a Euler equation describe motion, describe action of this group, and therefore has geometric meaning and cannot be modified. I will write it down now. It's Euler in viscid fluid is a Hamiltonian system. And remarkable property of so Hamiltonian can be written. It's very simple. Poisson brackets could be written. It's very simple. It's in a textbook. But if you ask to write an action, and then from this action derive Hamilton principle, and Hamilton principle is to find a good configuration which minimizes the action, that has been postponed by 200 years and written recently, relatively recently, by Arnold in 1996. So it's not hydrodynamics could be understood in various different ways. First of all, I write differential equation. I would like to solve it. That's one story. We are not interested. Second, we would like to understand geometry of that equation or kinematics. And kinematics of this equation, because it's related to complicated group, it is complicated and not fully understood. And that's my story about. So, but let me start by writing equation. So I will write a non-relativistic equation, although it does matter relativistic or non-relativistic, but I will write non-relativistic equation because it's easily recognized. It's in the first page of any textbook. So equation is the following. So fluid characterized by density and velocity. It's in 3 dimensions. So equation I will write and then we discuss. That's equation written by Euler. There is some, like, I have to give you 10 minutes crash course on that, what is what here, because otherwise I can proceed. So that's a density, that's velocity. P is the pressure. And gradient of pressure is a force which acting on the small piece of a fluid. dt, it's time derivative, and it's called material time derivative. It's not only partial time derivative, but plus a fine connection related to the flow. With that, equation becomes nonlinear. So it is bilinear in velocity, and therefore that's how it is. So it's highly nonlinear motion. It's a velocity v times delta. It's times nabla. Now, pressure is something may depends on the density, and it's something given by chemists. Chemists tell me how this pressure depends on the density or other thermodynamic quantity. It's an input to this equation. As it's written, it's a Newton equation. That's acceleration, mass, acceleration of atom, acceleration, force. It will be convenient for me to introduce the following notation. So instead of density, I will use particle numbers, and that's mass. Mass of atom, how many atoms, density, mass density, that stays here. Right, so and I will operate in this n. Integral of n over space, its total number of particles in the fluid. So n itself would be understood as a three-differential form, such as I will integrate over volume. It's a volume. I will get a number of particles in the fluid. Right. Then out of velocity and this n, I will construct also three form. I will write it as it's a three form, four form. It's space-time, which consists of number of particles. It's the first time-like component, and then number of particles time velocity, flux of the flow. I wrote it as one index, only one index, but it's actually three form, right? So the best object three form is it will be dual of Hodge dual of n. So we have to understand that there is a three form. Okay. In addition to that, fluid moves with certain momentum. Momentum. What is momentum? It's a four-component momentum, which consists of energy of element of fluid at rest, and then mass times velocity. And I'm talking about Galilean invariant fluid. So we have two canonical variables, n mu and n and p. That's a three form, and that will be one form. I call that p. One form. Sorry? No, energy at rest. At rest. No, if it's Galilean fluid, it's energy at rest plus v square over plus kinetic energy. Okay, so in 1941, relatively recently, compared to Euler, French differential geometer Andrei Lichnerovich managed to rewrite this equation in this canonical Eulerian fields without using a metric. The way how momentum and particle current related to each other, they related to each other parameterized by velocity. It's called equation of states. But if I consider P and N, three form and one form, independent, regardless of equation of states, I will not impose a relation between them, then this equation can be rewritten in a very interesting way, such as metric is not involved. That's Lichnerovich. That's a kind of remarkable story because then that equation becomes part of the differential geometry. Sorry? And therefore, written in terms of n and p, equation becomes independent of metric, and it's the same for relativistic, non-relativistic. You bring a distant star, gravitational star, doesn't matter, metric out. If variables are chosen right, and this is two canonical variables, I will not speak about a little bit more, but I would like to emphasize that this equation looks like a Newton equation, but actually becomes part of the differential geometry and stays in now sort of moved from a book about differential equations, partial differential equation, to the book of differential geometry. This is how we studied. Okay, just to show how it looks, I will introduce two more objects. I will need two form, which is called vorticity. which is exterior derivative of momentum. Momentum is one form. And also I will need helicity. It's called vorticity. And that's called helicity. I will use forms. Helicity. So this is a two form, sometimes called Poincaré two form, and this is also three form. Well, fluid has then Lichnerovich equation. This equation could be written in the following interesting way. So I don't know whether people familiar with exterior product, but anybody familiar with interior product in differential forms? It's usually called labeled by iota. And it's an operation which converts, say, two form with one form and obtain one form. So it's a kind of tensor product. So that equation could be rewritten in remarkably interesting form. Sorry? It's a vector field. Yeah, I will write it. I will write it now. Let me write n times u mu. That is for velocity. And then for velocity means one vector field. It's a vector field. And this vector field contracted with vorticity field equals 0. That's Lichnerovich form of Euler equation. It's entirely geometric relation between, so we have a vector flow characterized by a vector field U, and fluid moves such that vorticity field contracted with U vanishing. Sorry? In indices, it's the following. It's indices in the following. I will write it in indices. Right. So this will be vorticity projected to the flow, vanish. Why I'm telling you this? It's a whole story. It's a story for a year course. But I'm telling you this that when we think about hydrodynamics, we have to think about differential geometry. Okay. In what I'm going to say, helicity. In what I'm going to say, helicity plays important role. So let me explain physical meaning of helicity. Sorry? Okay, so let me explain. First of all, let me start from vorticity. In fluids, there are vortices. What is vortices? It's a singular line in three-dimensional space and fluid circulating around these vortices. If, by the way, if circulation is integral of around this vortex of momentum one form of this of momentum one form, where is my form? So you can integrate one form. Again, in 1941, Ansager reported to mankind that this circulation in quantum fluids always quantized in units of Planck constant. That's called Ansager quantization. This fact has been Anzeiger, 1941. This fact has been experimentally verified and is one of the fundamental facts in physics. That tells me that momentum space, which is a phase space, which in quantum case is compact. In classical case, not, but in quantum case, it's compact. And that's important fact of geometry. Also, phase space consists, what is the dimension of the phase space? Of course, it's infinite dimension, but it's a given point. For example, what is the rank of cotangent bundle? It's a four-dimensional space, but rank of the tangent bundle is 4, but rank of the cotangent bundle is 5. So we have four momentum, energy, and 3 momentum, 4, and we also have this n. So dimension rank tangents. How many fields, how many differential forms are there? It's 5. And that's 5 play important role in what I'm going to say. So vorticity tells me about circulation. This circulation by Gauss, by Stokes formula, can be written as an integral of the two form of that surface bounded by circulation, right? Okay, but helicity is a little bit more interesting object. It's the following thing. It's fluid is not only circulating, but also spiraling. And number of the spirals, it's an integral of the helicity. You not have to integrate over two surfaces, but you also, to count number of twists, you have to also integrate it along this one. And that for that you need a 3 form. The 3 form. Okay. Vortices. In space, in a closed space, if the manifold is closed, no boundaries, vortices always form loops. They can't end and begin. It means that there is no monopoles, vertical monopoles, sources of vortex. Of course, if there is a boundary, the vortex can start on the boundary, end of the boundary, but no boundary, it's always loops. One may consider the following question. Suppose I have two vortices, two vortex loops, and then I put a spoon in my fluid, move this spoon such that these vortices move and change their linking number. That's a linking number. This is topological invariant, but with the help of the spoon, I can do something. If I drive the system, I can change the topological number. So what is this number? And apparently that's an integral of helicity. That's integral of a 3-dimensional space of the volume. That will be total helicity. That's twice of linking number of vortex lines, vortex loops. Linking number of vortex loops. But both those familiar with Chern-Simons theory, you can recognize it's actually Chern-Simons term, but being integrated. But because the phase space is compact, this integral is topological invariant. And so on. If I take helicity and take an additional external derivative, that will be 4 form, and so there is only one 4 form in this business, which is varticity square. And that is, as we know, is called twice minus second Chern character of the cotangent bundle. I don't know how to say it. Space. Well, I write it this way. This way. Right. Then if I integrate Chern number over space-time, that will be an integer, that will be a helicity. This integral tells that no matter what I do with my spoon, if I compute that integral over space-time, I simply count change of linking number. Today, linking number 0, tomorrow, 1. Okay. A little bit about topology. Linking number is not easy to destroy. If a fluid lives by its own, linking number forever will be forever there, but with a spoon, it can be moved. Okay, so I have an incredibly complicated task in limited time to describe this mess of information. Why I'm telling you this, I will use this fact, but would like to say is that from differential geometry, it's now the subjects move to another domain of topology and cohomology. Okay, so I write this equation again. Equation, and we can count how many degrees of freedom here. It's a 3 velocity, pressure, and number of particles, 5. I don't know how to call it. That's a contracted vector, right? It's nabla derivative. It's contracted number. I'm sorry. And this is a sorry. Time derivative. Yes, and time derivative that is, I don't know, bolt base. That's, I don't know. It's okay. It's okay. 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 So yes. So there is a five objects here. It's 4-dimensional space, but 5 objects. So to make this equation close, we need one more differential equation. And that equation is called continuity equation. It's a time derivative of n plus nabla of nv vanish. Now the system is complete. Right? Better to write it in these terms as a divergence of this vector field of this reform vanish. Now the system is completed. Okay, that's a short excursus in. Now let me come to anomalies. Arrays. By the way, energy and pressure are related by Legendre transformations. If you know one, you know another. There is a Legendre transformation. The formula is something like that. Okay. Now I would like to. I move to another subject. And Anton, what is my time? Now this subject. Consider Dirac Fermions. Coupled with external gauge field. And for simplicity, for the sake of this talk, I assume that it's U1. That is called quantum electrodynamics. Dirac-Fermi electron is a column with 4 entries, and 2 of them called while fermion right movers and fermions left movers. Each of them has spin up, down, up, down. So altogether it's 4 column. Now Dirac-Lagrangian of Dirac field, which is psi, psi, and maybe I will add external gauge field. Being written in components, decoupled of 2 independent pieces, Lagrangian for the right movers and Lagrangian for the left movers. Each of them absolutely independent and equal to no master free. Mu psi. And sigma mu, it's a right movers. It's a 2 by 2 matrices acting only on spin of right movers, same for left. And that is called Pauli matrices. This is 3 Pauli matrices and 1, and this plus minus for the right and left movers. Okay. Both are in. Okay, so because they're independent, one may think, yes, okay, in addition to description of this Dirac particles in terms of particles, quantum field theory, particles. It's convenient to introduce currents. And these currents, psi, psi, which consists of right mover and the left mover. Or one can say that this is right current, and that is left current, plus left current, right current, left current. But current of right particles, current of left particles. Alternatively, we can consider a difference between them. And that's called axial current. If you're not familiar with these notations, it doesn't matter. So it's physically clear, right movers, left movers. Physically, what right movers means? If particle move in this direction and this is its momentum, then it has a spin. And spin always, according to Dirac equation, always directed along the motion. If it's directed along the motion, that's a right mover. But if it's directed opposite the motion, that's a left mover. That's momentum. That's what it means. Okay, because of gauge, because they're completely separated, one can say that gauge invariance requires that each of them, each of the current, right, or left, should be conserved. That's a gauge invariance. And currents are neutral current of U1 cross U1 right and left symmetries, and they divergence free. However, in quantum field theory, it's not the case. And what happened in quantum field theory is the following. So it's the vector current, which is carry electric charge, is conserved. And that we know not from quantum field theory, it's a kind of, we know it's from Faraday. Faraday told us that electric charge is conserved. So this is necessary, must be this kind of experimental fact. Quantum field theory must be defined such that it's true. But if that happened, then the fifth current, the axial current, is not conserved and equal to Maxwell tensor F mu nu times Maxwell dual Maxwell tensor. And K is the integer parameter which tells how many species of these fermions they may have flavor, and that is this how many of them. That is called axial current anomaly. Axial current anomaly, and it's non-perturbative result. It's kinematic of electrons. And it's sort of embedded in the definition of quantum field theory of fermions. The story is that Lagrangian, although decoupled into pieces, independent pieces, but Hilbert space does not. And that's indication about Hilbert space. That's why it's non-perturbative. So that story, interpretation of that story is the following. As you know, that is minus twice Chern, second Chern class of U1 bundle. And therefore, its integral is topological invariant called Chern number. We may integrate this thing over space-time, but over in cylindrical geometry. Say time runs here, and that is space, says compactified three-dimensional space, say spheres. So I would like to integrate over the geometry. So I start from this number. From this number, if I integrate that number, that cylinder, I will find number of right movers minus number of left movers. That's axial number of particles. Taking in the beginning of the process and in the end of this process, subscribe, it's change from here to here in time. It's time equals 0. It's time equal t. That's integral of the left-hand side. Integral of the right-hand side is a Chern number. Right. Which is an integral of over space-time. Okay. Now, let's the field configuration which gives that non-zero value, sometimes called instantons. But that's usually applied for non-abelian cases, non-abelian field. But in abelian field, it has a very simple interpretation, is the following. Let's assume that I take my electrons and put it in magnetic field. And magnetic field in quantum world, as we know, consists of flux tubes. Each flux tubes carry flux quantum, Planck constant, EC, right? Just one. Planck constant. CE, right? Okay.
Sharp or is sharp?
E is a charge. It's a so it's if E C equal 1, that is 2 pi h bar times integer. Again, that comes from the fact that there is no Dirac magnetic monopoles. So the flux here is quantized. So whatever magnetic field is, how maybe very smooth, it always consists of flux tubes in quantum world. So let's consider two of those flux tubes. That's a flux of magnetic field. So magnetic field is inside, no magnetic field outside. And then another flux tube. So what this formula says, that the change twice change over linking number of magnetic flux tubes. So if I put my electrons in the magnet, and then I have a device, I change the magnetic field back and forth such that two magnetic tubes linked or relinked, this number change. So what it means? It means that if there is a 15 particles which moving, this is the momentum with spin aligned the motion, that's the right movers, and then some number of particles which has the opposite spin. Then if I linked these two flux tubes, magnetic field, then one particle decided to move from the left camp to the right camp. So it flips the spin. And therefore, number of left particle movers will be decreased by 1, and number of right movers will be increased by 1. The difference changed by 2, and that's exactly 2. People spend about 30 years computing these two by computing triangle diagrams.
Yeah. So
This diagram is equal to this 2. The diagram diverges, it's infinity, or depending on regularization, you can give it any value. And a generation did this crap without understanding that they computing an integer. Now no computation is necessary. We understand what's going on. Okay. Now that's quantum, that's anomaly. Okay. Now I take quantum fluid. For example, a good quantum fluid is helium-3. Helium-3 consists of fermions because helium isotope is fermions. And I know that collection of fermions, Dirac fermions, form a fluid. It's one piece of knowledge. So I open Arnold book and say, if it's fluid, helium obeys this direction, this equation, and this equation. Book, I say that because it consists of fermions, there must be anomaly. And this interesting property, when I manipulate by magnetic field, I can change the polarization of electrons. So if all is right, that formula must follow from this equation. Because that's fluid, and fluid is built of fermions. And this is fundamental property of fermions. Subject. That's what we thinking about. Of electrons. In this formula, it's information not about dynamics, but about a Hilbert space of electrons. one story. Then experimental colleague tells me that fermions sometimes form fluid, not gas. If so, they must describe by current algebra, because current algebra is hydrodynamics. That's an example of current algebra. Where is this equation here? That's the question. Raised in recent years about I don't know what my time is. Over 3 minutes. So there is a machine in several countries which called heavy ion collider. Heavy ion collider. People collide heavy ions, say gold and I don't know, uranium. They produce mesons and stuff. And in a short time, there is a magnetic field. So they think about quark-gluon plasma in magnetic field. If it's quark-gluon plasma and this is quarks, it must be. And anomaly means a lot. For example, if one of application of anomaly is a process of destruction of baryons, it's called baryogenesis. If we took proton and neutron, there is a small probability that it's decouple, that it's eliminates themselves and produce two leptons, it's a positron and right electronic neutrino, baryons to leptons. That's a consequence of this formula. So it's a pretty fundamental story, which has entirely topological interpretation of linking, relinking of magnetic lines. So where is the story here? That's the question. And the answer is no, it doesn't happen. There is a lot of topology in this equation. I explained, so there are vortex lines, they form loops. Loops can be linked, relinked. There is also a Chern class, which is called divergence of helicity. Many similar, almost identical geometry, but not happened. So the question now is this possible to modify this equation such they will describe that phenomenon? But that equation, for example, if you take helium-4, which built out of bosons, bosonic isotope, there is no such thing. And there is a full consensus, deep consensus that Euler equation describe helium-4, but not helium-3 built out of fermions. So how shall we, is it possible to modify this equation to describe that story? That's the subject of current focus of current research. And its attempt to modify this equation hit a wall. Because as I discussed in the beginning, this equation are not for nothing. It's entirely reflect a property of diffeomorphism of space-time. And simply cannot be modified because it has a geometric origin, or cannot be modified easily. So the question is there any room to do something with them, to match a property of the Hilbert space of electrons? Fundamental question. And that's what we do now. And I will happy to tell you how it works, but my time is over. There is an answer. Maybe I can write an answer. There are two equations here. This equation cannot be modified because it's built out of diffeomorphism. But that equation is a Noether current associated with U1 gauge symmetry, and that could be modified. but modification must be such that the total number of particles will be quantized, right? Particles are quantized, 1, 2, 3, 15. So if it would be modified, so the right-hand side must consist of given integer. So it must be topological. And there is only one. And that invariant is arbitrary integer coefficient, and then wedge product of vorticity. And this is vorticity. Vorticity, I recall that vorticity is dp. After that modification, you may say that we are interested in charged particles, plasma. Then I have to modify this equation by adding electromagnetic field. And that modification, when magnetic field is added, produce precisely this equation, right? So, and the next point is to prove or to understand why this modification is unique, possible. And that's entirely different story. But intuitively, it's almost clear. Fluid dynamics do not supply other topological invariant matrices, right? So with that fluid, you do the following. You have a box of particles with a small door, open system, like door to the balcony, like here, door to the balcony here. And then you put a spoon in this fluid, start to move it such that the spoon creates vortices. And then another turn of the spoon, you link or unlink the vortices. And suddenly, two particles go out of the room. It's particle production. So the spoon will produce particles or suck them, invite them out of the street to the room or push them away. Right? And that's what's the geometrical meaning of this equation. Right? So it's so rigid. It's so rigid. So there is no move. Every attempt, there are probably several hundred papers written on that subject. Most of them are wrong because they try to modify equation, and the equation is not modifiable because they have the geometric background. You can think about differential equations, then you can play with them, but it's not differential equation, it's a geometric statements. Yes. That phenomena does not sensitive to equation of states. As well as anomaly. No, there is no equation of states here. No. Yeah, it's all written in terms of this Lichnerovich approach, which metric independent. It is written through vector field and one momentum differential form. When you ask me how n depends on momentum, that's equation of state, but it's not enter. Topological argument goes beyond it. It's metric independent. Same as here. So we know that anomaly is non-perturbative. It has been historically derived for free fermions, but then in another 20 years, people try to understand why interaction doesn't matter. And Hofts was the champion of this. Right? They look for equation of states and found that no, it's obtained by simple calculation for free fermions, but it's true for anything, for always, because it's a property of Hilbert space, not dynamics. And here it's a property of geometry, not dynamics. Dynamics is equation of state. Metric. Sorry.
Okay, more questions.
Sorry?
If there is something like this in less dimensions, not fourth dimension?
That story happened in any even dimension. If you go down, we can go to the sixth dimension. Then we will talk about intersection theory of surfaces, how surfaces intersect in high dimension, right? Generalization. If you go down to 2-dimension, then we know what happened. It's called bosonization. So people some time ago discovered that 1 + 1 dimensional fermions could be bosonized, so-called. What does it mean? It means written in terms of bosons. What bosons are? They're currents. If they're currents, it's fluid. And then the story happened. In 1 + 1, it was known, but not in the term which we describe it now, but in some messy terms, it was known in 1 + 1.
Okay, more. Let me check if there are some on Zoom. Okay. If not, then let's thank the speaker again.